So, good evening. Welcome to Krishna's classroom. We continue from where we left last time. We are looking at some examples of complete spaces. And we proved that if X is a non-empty set and Bx is the set of all bounded real value functions or even complex value functions with the sup norm, so then you know that the sup norm makes sense. Then this is a complete non-linear space, and therefore it's a complete metric space. Here, of course, we have taken X as a non-empty set. Now we look at another complete non-linear space, which often appears in analysis. This is the Cx norm-empty. So C. Now this consists of all. So here we make an assumption that assume X is a compact space. Compactness is important here. Now consider all continuous functions. So Cx, the set of all f real value on X and continuous So these are the functions that we consider, and one can easily argue that it's a bounded function and it's a part of this, and with norm f defined as supremum of this is a norm on Cx, and therefore Cx and therefore a metric space. Now what we assert is that this particular space a complete So we shall state the theorem. Let X be a compact matrix space then the normed linear space of all continuous real as well as complex or complex. Now I'll make a remark about this later, but for the time being, let me just real valued functions is, that's a statement. Okay, first of all, we observe one thing, fall back on first theorem. So when we work out the proof, see, we fall back on the following result, that since X is compact, all continuous functions bounded. That's the first thing that we observe, comes from the compactness of the space. This we have already seen. Now what we, therefore, and that implies Cx norm infinity, makes sense, is a part of Vx infinity. So it's a subspace of that. So Cx is a subspace of Vx. That is the first observation. Now you see, we have already proved that Vx is complete. We have already seen that therefore Cx norm infinity is a subspace of Px infinity. Now what we are trying to prove is that, and our objective is to prove that Cx infinity, norm infinity, is complete, and Cx is, well, I'll just write here. Complete. And is complete if and only if is a closed subspace of infinity. So what we need to prove, or it is sufficient to prove that this is closed. So we claim, so instead of proving completeness, it is sufficient to prove, because we have already seen that if X is a complete metric space and E is a subset of that, and then E is complete then only if it's a closed subset. Yeah. So we have to prove Cx norm infinity is closed. Px norm infinity. So let Fn be a sequence of functions infinity. Norm infinity converging to F belonging to so what it is sufficient to show that, then we claim that f belongs to. So if there is any sequence in Cx norm infinity which is convergent to some f, then of course obviously it is going to be a element of this, because all convergent sequences, because you can consider them as convergent sequences in Vx norm infinity, and you see that the Vx norm infinity is complete. Therefore, this sequence, the convergent sequence converges to some element in Vx norm infinity. I mean, that's clear. But what we want to say is that it is inside Cx norm infinity. So it is sufficient to prove that the limiting function is a continuous function on x. That is, we have to prove that f is a continuous on x, so that it is this is what we want to prove. Okay, so it's just checking the continuity of this, and that's the usual way of doing it. So we check that it is continuous at each point of x. Let us prove this. So let x naught be an arbitrary point of x. We prove that f is continuous at x naught. Okay. So let epsilon positive we know that all the xfn's are continuous at x naught. That's the information that we have. Further, we have norm of fn minus f goes to 0 as n tends to infinity. That is, mod fn x minus f of x goes to 0 for every x belonging to x. as n tends to infinity. So that follows from this. Therefore, you see that the convergence is uniform. Uniform. The reason is this. See that mod fn x minus fx is less than or equal to norm of infinity, and this goes to 0. Therefore, it is uniform. What does it mean? That is, there exists n belonging to the set of natural numbers such that greater than or equal to n, and for all case. So we have obtained a particular n associated with. Now we want to check the continuity of f at the arbitrary point x0 that we have chosen. So let us explore that. Now fn is continuous at x0. Hence, we just use the definition of continuity with the same epsilon. For the same epsilon, we have there exists a delta positive such that if x belongs to the delta neighborhood of x0, rather contain x, then we have mod I think it's fn epsilon by 3. So this is merely applying the definition of continuity at the point x0. Now we will estimate this. Therefore, mod this is what we want the continuity of this. Now you see that using triangular inequality we get And that is add and subtract fnx and fnx naught. And then apply the triangular inequality. This is what you and you see that this is less than epsilon by 3 plus the second term is also we have seen that less than epsilon by 3 plus the final term is also epsilon by 3 epsilon for every x inside x. Okay, so therefore you see that what we have proved is that f is continuous at x naught. Since x naught is arbitrary, it follows that f is continuous at every. Follows that f is continuous on x at all points. Okay. Therefore, f belongs to that is a closed subspace of the complete space which implies that completes the proof. So we have seen two significant examples of complete spaces that we often come across in analysis. Now just observe that here X is taken as a compact metric space and continuity plus compactness of the domain assured that it's a bounded function. And in the case of dx norm infinity, we didn't make any assumption of that kind, or we didn't need any assumption of that kind, because all that we assumed was that all the functions that we take are all bounded functions on the space. Now, one of the remarks is that in both these cases, one can one can consider complex valued functions on X and prove the same results. So that's a worthwhile observation. So it's only just for transparency. We started working with real value functions. So that completes the proof of that theorem. Now we shall look at some applications. Take x to be equal to 1 by n zero. Now you know that this is a part of the real line and x is compact. Now consider Cx continuous functions defined on continuous real value or complex value. You can use either defined on X. Now what you get then is this. See, what is f? So define f to be, what is f then? And f can be conceived as a sequence. And what kind of sequence we will see now. We have f1, f and so on. And we are assuming f is continuous. Therefore, f 1 by n goes to f 0 because of continuity. Since 1 by n so this can be conceived as a convergent sequence. So this space, what is that? Cx C, the space of convergent sequences. Now apply this theorem. So you consider, see that you consider all bounded sequences. So you see that this is a part of C is a part of bounded sequences. What this thing I can say? Okay, some L infinity. C is a part of L infinity. and you know that L infinity is complete. Therefore, C is conceived as a continuous function on this compact set, and therefore, see, C is that's our. Okay, we make another result. Another example. Let f from be continuous on to map. Assume is less than or equal to dy of for x1 belonging to x. Then if x is complete, so is. See, this is quite easy to prove. First of all, you observe that therefore f is a one-to-one onto map one-to-one map onto so it is both one-to-one and onto. Okay. Now what is that you want to prove? You want to prove that y is complete. No? So what do you have to do? In y, you choose a Cauchy sequence and show that it is convergent in y itself. Okay, how do you prove that? So you start with a Cauchy sequence in y. Because Cauchy sequence in y is they are just of the form fxn. Okay. Now there is a corresponding sequence here, xn. Now this is assumed to be quotient. This is assumed to be quotient means this implies xn is quotient. So what we have is this. Start with a sequence, a Cauchy sequence in Y. So we start with a Cauchy sequence in Y. And then we obtain a Cauchy sequence in X because of that inequality. They are going to be of the form fx because for xn belonging to, now what do we have? Consider the sequence xn. Now use the inequality under the condition and you see that since it follows that such that less than epsilon for every n m greater than n epsilon. Which in turn implies using star, using this inequality, which implies what? That implies xn is quotient. And X is complete implies as n tends to infinity. Then f of x belongs to y by continuity follows that which implies the Cauchy sequence so that proves the completeness of y if x is complete. Okay, I think we stop here for the day and take up what is called the nested interval theorem in our next lecture. So that will be the main theme for our next lecture, the next nested interval theorem. So tomorrow possibly we meet, I hope, evening sometime, find it convenient to meet. Thank you very much. So good night, have a nice evening. Yeah.